Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical specs to the most practical ones. So if this is the first video that you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present Bisphenol-F Epoxy Resins. Bisphenol-F BPF is an organic compound with a chemical structure similar to bisphenol A, belongs to the category of molecules known as bisphenols, which features two phenyl groups connected via a linking group. It's a white powder with a boiling point of 390 centigrade, density of 1.2 and molecular weight of 200.23 gram per mole. It's a white powder, and in BPF, the two aromatic rings are linked by a methylene connection group. The IUPAC name of bisphenol F is 4,4'-dihydroxy diphenyl methane, and its Cas number is 62092/8. BPF is used in the manufacture of plastics and epoxy resins. It is used in the production of tank and pipe linings, industrial flooring, road and bridge deck topping, structural adhesives, grouts, coatings, and electrical varnishes. BPF is also utilized in liners, lacquers, adhesives, plastics, and the coating of drink and food cans. BPF is also found in dental materials and tissue substitutes. Regarding health concern, it should be mentioned that based on the ECHA database, this substance causes serious eye damage and may cause an allergic skin reaction. It has also been considered harmful to aquatic life with long-lasting effects. Available data for BPF show clear and consistent adverse and population-related effects on reproduction and sexual development. Data clearly and consistently demonstrate an estrogenic and anti-androgenic activity of BPF. BPF may have multiple modes of endocrine action: estrogenic, anti-androgenic, thyroidal activity, and interference with estroidogenesis that might interact and are difficult to distinguish from each other. Bisphenol F is produced by the reaction of phenol and formaldehyde. This reaction takes place in the presence of catalyst, which is acid plus water, and the unreacted phenol from the product to give a crude bisphenol F, and next the acid catalysis is removed. A part of the crude bisphenol F is distilled to give a highly pure bisphenol F. To give bisphenol F for general use, highly pure bisphenol F is mixed with the remaining crude bisphenol F. The synthesis of the glycidyl ether bisphenol A resins has been discussed in another session. To recall, let's repeat the epoxy resins derived from epichlorohydrin are termed glycidyl-based resins, and diglycidyl ether bisphenol A can be produced either through a process called TOFFI or through a method called advanced method. For further information, please check the other video on diglycidyl ether bisphenol epoxy resins. Bisphenol F is similar to bisphenol A, except phenol is reacted with formaldehyde rather than acetone. The resultant phenolic chemical does not have the two methyl groups that are present between the ring structure in bisphenol A resins. Bisphenol F is reacted with epichlorohydrin to form the glycidyl ether bisphenol F resins. Because of the missing methyl groups, the viscosity of bisphenol F resins are typically 1/3 of bisphenol A resins, 2,500 to 5,000 centipoises. Additionally, there is a higher portion of three functional epoxy molecules, which increases the functionality available for cross-linking from 1.9 to 2.1. Moreover, the chemical resistance of diglycidyl ether bisphenol F resin is comparably higher than that of diglycidyl ether bisphenol A resins. There are two main reasons for their higher chemical resistant properties. First, bisphenol F systems have a slightly higher functionality than Bisphenol A. The higher functionality provides more reaction size, leading to a tighter and more three-dimensional cross-link density. Cross-link density determines chemical resistance. Second, relative to Bisphenol A resins, Bisphenol F resins have lower viscosity. Lower viscosity means fewer additives and diluents are needed to enhance application properties. Additives and diluents diminish the cross-linking density, which in turn lowers the chemical resistance of the epoxy systems. The differences between diglycidyl ether bisphenol A and diglycidyl ether bisphenol F resins have been shown in this figure. The bisphenol F compound is obtained by the reaction of phenol in excessive amount of formaldehyde, as explained earlier. Yet, here is repeated to emphasize on the fact that there are different isomers produced, which have been shown in the presented chemical schematic. Briefly, diglycidyl ether bisphenol F is synthesized by three different structural isomers of bisphenol F. So we have DGEBF, ortho-para, and ortho-ortho diglycidyl ether bisphenol Fs, in which technically just the position of the OH group differs among them. Studies among isomers suggest Bisphenol F epoxies consisting of higher concentration of para-para bisphenol F may have superior thermal stability compared to the other isomers or mixes. This epoxy resin is also produced in a similar fashion, and if it is synthesized from the phenyl formaldehyde and epichlorohydrin, oxalic acid is used as a catalyst. Commonly, resins had epoxide number of 0.65 to 0.68 mole per 100 grams and a viscosity of 1.3 pascal second. Regarding the comparison between the BPA and BPF epoxy resins, one common fact is that the Bisphenol F resins often have a comparably lower viscosity and also are a slightly higher functionality than Bisphenol A resins. When the two methylene groups are not there, the molecular weight is lower for the same amount of active groups, which result in higher functionality. The presence of bisphenol F in the structure of the diglycidyl ether bisphenol F resins does not adversely affect the mechanical properties of the cured thermosets. Therefore, the mechanical properties of diglycidyl ether bisphenol A and diglycidyl ether bisphenol F resins are comparable. Moreover, diglycidyl ether bisphenol F resins have a similar chemical reactivity compared to liquid bisphenol A epoxy resins. Crystallization is often a problem with liquid bisphenol A resins, and this can be reduced with bisphenol F resins. In terms of crystallization tendency, it should be noted that bisphenol F resins perform very well. Compared to diglycidyl ether bisphenol A, the Bis-F component has a lower tendency for crystallization and can be used for application where crystallization might be an issue. If diglycidyl ether bisphenol F resin develops haziness or crystallizes during storage, it can be restored to its original condition by gently warming the container, and it contains to approximately 170 to 190 Fahrenheit until all visual evidences of crystallization is gone. Upon cooling to normal ambient temperature conditions, the product will regain its original liquid state physical properties. This process can be repeated as necessary. There is also a possibility of making bisphenol A and bisphenol F resin blends, as the good established track record as a crystallization inhibitor for liquid diglycidyl ether chemical reactivity, and also the chemical structure of both compounds are kind of similar. This way, diglycidyl ether bisphenol A can be modified. Consequently, non-crystallizing liquid epoxy resins, which are blends of diglycidyl ether bisphenol A and diglycidyl ether bisphenol F epoxies, are available. To sum up, to modify diglycidyl ether bisphenol A resins for reducing the viscosity or inhibition of crystallization, diglycidyl ether bisphenol F resins are employed. It is worth mentioning that as the solid content of diglycidyl ether bisphenol F epoxies is 100, therefore the blend has no VOCs. Chemical products containing diglycidyl ether bisphenol F resins are quite widely used and may often be found in metal or concrete paints lacquers and other coating agents, adhesives, glues, bonding agents, flooring products, composite materials, and injection resin used to repair concrete cracks. Some studies have shown that BPF has liver toxicity, and the health concerns regarding BPF have been explained earlier in the former slides. Here, the spot is an epoxidized product. Epoxy resins are among the most important causes of occupational allergic content, dermatitis. Bisphenol-F epoxy resin structurally resembles the glycidyl ether bisphenol A resins, and they are often used together in a product requiring chemical resistance. That's why, when we consider the health effect of the glycidyl ether bisphenol F resins, we should also think of the concerns that may arise due to the presence of the other resin. In general, the health effects of both resins are comparable. Current studies have shown that the most health concerns belong to the presence of the epoxy group, especially terminal epoxy groups, and the backbone might have less impact, which explains why the health concern associated with the glycidyl ether bisphenol A and the glycidyl ether bisphenol F rises are alike. However, studies show there is a cross allergy between the two chemicals. These reactions to diglycidyl ether bisphenol F resins occur especially in workers handling composite products. The majority of allergies are work-related, and it belongs to the component causes of occupational allergic content dermatitis in some countries. At home, biocomponent glues or boat paints can be the cause of desensitization. There are also allergic reactions with no apparent relevance. A relationship between fragrance allergy has also been observed. In occupations with heavy exposure to uncured epoxy products, sensitization often occurs with a few months after entering the trade. Hand dermatitis is a common symptom, but facial symptoms are almost as common. The dermatitis usually heals if the exposure stops, but many patients need to change jobs. Generally, exposure to these epoxy materials should be minimized and avoided if feasible. When handling, through the observance of proper precautions, the worker should use appropriate engineering controls and proper personal protective clothing and equipment, and adhere to proper handling procedures, which are often provided in the SDS document. When handling and during work with Bisphenol-F epoxy resins, we should protect ourselves and obey the safety conducts. You need to protect your hands from epoxy resins and hardener liquids. Proper gloves types could be nitrile gloves or latex gloves. You also need good ventilation in the work area, and also it is good to wear a plastic apron. For example, a PVC apron can be a good idea. You should also use safety goggles and wear a respirator. One should have access to the SDS documents of the resins at all times and for emergency cases. The liquid Bisphenol-F resins have low viscosity, so they excel in workability and moldability, which makes them suitable to be used in many applications. These types of epoxy resins can cure at room temperature and also under heat conditions. The viscosity of the liquid Bisphenol-F epoxy resin is in the range of 4,000 to 6,000 millipascal seconds, almost 1/3 of Bisphenol A resins, and the EEW is around 165. Epoxy resins based on Bisphenol F are used primarily as functional diluents in applications requiring a low viscosity, high-performance resin systems, for example, solvent-free coatings. Higher filler levels and faster bubble release are possible because of the lower viscosities. The higher epoxy content and functionality of Bisphenol-F epoxy resins provide improved chemical resistance compared to conventional Bisphenol A epoxies. Generally, unmodified Bisphenol-F based epoxy resins have very good chemical resistance and good mechanical properties and are lower in viscosity compared to Bisphenol A based resins. When properly formulated with Bisphenol A, They help reduce crystallization tendency and find application in adhesives, laminates, coatings, and civil engineering. Regarding the curing, Bisphenol-F epoxy resins react with a full range of epoxy curative, and the whole spectrum of curing agents can be employed. When Bisphenol-F epoxy resin is cross-linked with appropriate curing agents, superior mechanical, adhesive, electrical, and chemical resistant properties can be obtained. Generally speaking, the performance of Bisphenol-F epoxy resin is comparably better than the performance of Bisphenol A epoxy resins. More specifically, in the adhesion, both resins perform excellently. Both resins are kind of weak in terms of UV protection. For VOC category, Bisphenol-F epoxy resins are generally better as no diluent are required to modify their viscosity. In terms of crystallization, as it has been mentioned several times, the Bisphenol-F resins are much better, and actually this feature along with the lower viscosities are the main advantages of these resins over Bisphenol A epoxy resins. Both resins perform well in terms of moisture resistance, and Bisphenol-F epoxy resins outperform the other one in terms of chemical resistance. Bisphenol-F epoxy resins are used in high solids, high build systems, and are capable of being used in broad range of applications, including coating, civil engineering, adhesive, electrical insulating materials, and reactive intermediates. The application of Bisphenol F in construction is common as there is a need for high chemical resistance, especially in tank and pipe systems, floors, coatings, varnishes, and adhesives. Also, they're resistant to a wide range of chemicals, make them a proper candidate to be used when chemical resistance is a merit, especially for civil engineering and water treatment applications. Finally, it should be mentioned that the resin content must be balanced by formulators who impart other desirable properties by this means. Therefore, even with a pure Bisphenol F resin system, additives are necessary to provide the right surface appearance and application properties. USA is the largest market with a share of about 30% of Bisphenol F market, followed by Europe and Japan. Both have a share about 40%. In terms of product, we have different types of product in the market: low viscosity, medium viscosity, and high viscosity Bisphenol F resins are there. Among them, the medium viscosity is the largest segment, which is the share is nearly 50%. In terms of application, the largest application is in coating. Growing demand for coating, adhesive, composite materials, and electrical insulation materials around the world has had a direct impact on the growth of the Bisphenol F resins. Global Bisphenol F resins key players include Huntsman, Olin Corporation, DIC Corporation, Hexion Chemical, Luna Harse, and these five manufacturers produce almost 70% of the epoxies. North America currently occupies the largest market share of Bisphenol F resins, but however, due to the blooming electronic industry, economic growth, population, and per capita income in the Asia-Pacific region, it is estimated that Asia-Pacific region will be the leading in the near future. Thanks for your attention. I hope you enjoyed this video. Please share your thoughts, comments, and questions, and I will come back to you soon. Have a great day.